Hello, my name is João Pedro Augusto de Oliveira, and today I'm going to talk about atomic bounds. As you can see, there are exactly two cubic representations of oxygen atoms, right here. But wouldn't it just look better if they were 8? They had exactly 8 electrons around them. It just seems way more fitting, doesn't it? Well, nature agrees. And because of that, there's something called the octa-rule. You see, atoms always want their valence shell to have a total of 8 electrons on them. Or to be complete, in some cases like hydrogen, they can all have 2. But on this case here, oxygen is very basic. So what they're gonna do is simply, so they both can pretend to have 8 electrons, is just share those right here. And boom. No. You may think, wait, no, there's not right, there's just 4 here, so 6 still. But those here are being shared by that, so technically, this right here has 8, and this right here has 8. Neither of them gonna spend more time with those electrons because, well, they're the same atom, they have the same electron negativity, and even if they did, then if it's closing off, they just gonna share it equally. So, what you can see here is pretty neat. A normal natural bound, and this type of bound, the ones that they share electrons, is called covalence bonds. Now, there's another type of covalence bonds that you are going to find with non-metals like oxygen. See, because covalence bonds have usually with non-metals, but you can see something right here with another non-metal, that is hydrogen. However, hydrogen here has a way lower level of electronegativity. What does that mean is how much they attract electrons to themselves. On this case right here, they're gonna try to have complete, Hydrogen, as I said before, is an exception. They are fine with 2 electrons, and they have 1 here to share 2, so they all can pretend to have their full shells, Here. Pooh, covalent bond made. But the thing here is because oxygen is so much greedier, it has so much more electronegativity, likes electrons so much more, the electrons here are going to spend more time floating around oxygen, because this model here don't show completely how things work. Electrons are always moving around, So they're going to spend more time here with oxygen, because it's highly superior electronegativity. Making, basically, this oxygen here be partially negative, and the hydrogens partially positive. This effect is very interesting, and is what allows lipids to happen. We call that polar covalent bonds. Another interesting type of bonds, however, is called metallic bonds. And as you can see, it's responsible for much of the metal's properties. You see, as you can observe here, there's just a sea of electrons around, and I feel metal atoms too. And the reason that happens, the electrons are not bound exactly to anything, just floating around in a communist blue, is because those metallic atoms, they really aren't that powerful. They are really not greedy. They don't have a high electronegativity, so they're not really pulling electrons to themselves out that much, And because they all cancel each other, because they have the same force shield, they just kind of float around, Those atoms become positive, and the electron is just floating around, completely separated from them. Bind them still, because negative attract positive and positive attract negative. But they are not really truly that connected, but still the metallic bond here. It also actually gives a lot of properties that this here has, because you can see it gives the malleability of metals, the ability to change their form very easily. They are not really hard bound for something, they're not really bounded hardly to anything. So if you were to break something normally, they just shatter completely. Here they can just change the form because it's already that separated, like how liquid change and just go back together. Same thing happens here. That's also why they are so conductive. Though you may think they will not because of their lower electronegativity. It's actually that's the reason why they are that powerful, because they can freely pass through the electrons, can just of the external source of electricity can just go through easily, while doing more electronegative with an atom with a higher electronegativity, they will just take it for themselves, They are really greedy, they're gonna take these electrons, nor they the electrons are just going to flow that easily, Another case, too, between another type of bound is between metals and non-metals. I already showed you the bound between metals and non-metals and non-metals. So here the hybrid version here, the ionic bonds. Here, the ionic bound is very interesting, and the name might already tell away how it works. Well, in the ionic bound, you have here a little metal and a little non-metal. Here, as you can see, because of the octa-row, this one is very close to having a full shell. And this one, you could just lose one electron and it should be fine, really. Because it really wants to lose this electron here to expose its internal shell. This internal electron shell that then will become the valence shell, and it will be complete. So, the obvious choice here is give the electron here. And there will be no combat, there will be no connection, really, the two just sharing it. Because this one doesn't really want electron, its electron activity is just really low. It doesn't want that. It's way lower than that one, that just really wants electron. So, fine, right? Just stop there. It's just gonna separate forever. No, not really. Because this one here now has a positive. It's a positive ion. That's because it just lost an electron and don't gain one, so it's negative now. So because of that, and not because of a weird covalence bound thingy, but because of the electromagnetism, and because they're, both ions, they're gonna attract each other. They're gonna attract each other and put together. That's why it's called the ionic bonds. Between a cation and an anion, It's very interesting, really, and if you are wondering why it's all a cube, it's because if it was a circle, it would just flow away.